Okay, so welcome to the next part in this video in which we're calculating the variance of a hypergeometric distribution. So in the previous part what we did is we dissected the variance of the hypergeometric distribution down into the sum of the variance of these subscripted random variables, which are these random variables ascribing to each outcome a 1 or a 0 depending on whether the first ball which you picked, the IF ball you picked was a white marble or a black marble, and then we had the and then we've got this these terms with the covariances of these random variables. So there's an awful lot of symmetry in these random variables, basically, because this at the moment looks like a hideous task. We've taken the variance of one random variable and we've reduced it down to we haven't reduced it much at all. We have turned it into calculating the variance of n different random variables, and then these bunches of covariances, of which there are a huge number. N choose two possibilities here, the number of ways of choosing two different random variables, basically. So it looks like a nightmare. The thing is that there is an awful lot of symmetry, and the reason is that these random variables, these little xi's, if we remember what they are, we've got this abstract probability space, which is all outcomes of picking n marbles from our possibility. So remember, we have 1, 2, all the way up to marble W, and those are all white marbles, so these are all white marbles, and then you go on, you have marble W plus 1 all the way up to W plus B, which are all the black marbles. So these are all black marbles, and we're picking n of these, and I don't care what order you put them in. Just in this probability space here, you put in every possible outcome that there is, every possible way there is to choose n different marbles from this W plus B total marbles. So in this sample space, there are in total W plus B choose n different outcomes, and then we have these random variables, little x1 through to little xn, which ascribe you the number 0 or 1 depending on whether your first marble is or your last marble, or any marble in between. Remember, we have the x2, x3, all the ones in between. They will ascribe you a 0 or 1 depending on whether your ith marble is white or black. And we discussed that, okay, yes, in this probability space you have to pick a representative for each outcome. So for instance, if I pick the marbles 1, 2, W plus 1, W plus B, that is a possibility if n is equal to 5. Of course, I'm just doing this to make it look concrete, but for an arbitrary n, obviously you'll need to pick more or less than this. We only want one of these representatives in. I don't want you to put in this sample space I don't want this to be a separate outcome, basically. That is the exact same outcome as this, so you only put one of them in once. But how do you decide which permutation to pick? Well, basically just pick an arbitrary one. It does not matter for our purposes. You might like to put them all in order, i.e. put put them in a numerical order, so the lowest one first, then followed by the second lowest one, third lowest one, fourth lowest one, fifth lowest one, etc. That's as good a way as any. But you just want one representative for the n factorial different ways of writing the same choice of n marbles, basically. Okay, so we have all these little random variables, these x subscript random variables, and we want to calculate their variances. But firstly, to work out their variances, we need to say how are they distributed, and they're all identically distributed. So xi is going to be Bernoulli distributed. That's obvious because there's only two possibilities. It's mapping you onto 0 or 1. So all we need to know is what is the probability that you're equal to 1, and I need to show you that the probability that you're equal to 1 is a constant for all of these. So it does not matter if you're talking about x1 or x2, the probability of this being 1 is equal. Okay, and the reason is that the probability of it being 1 is the probability that the first marble is a white marble, and this is for x2, the probability of a 1 is the probability that the second ball is a white marble. But we've just said the order is effectively arbitrary. You could have you could have chosen the representative in an arbitrary fashion. So the probability that the second ball is a white marble is effectively going to be exactly the same as the probability that the first ball is a white marble. So xi, they're all going to be distributed with the same probability. So it does not matter, basically. The probability of having a white marble in the second position is exactly the same as the probability of having a white marble in the first position. Okay, so what is the probability of having a white marble in a certain position? Well, that's just the probability that if you pick a marble at random from this bag of W plus B marbles, so we've got a bag of containing these white and black marbles. So here are the marbles, and you've got W white marbles and B black marbles. So what's the probability that if I pick a marble at random, I'm going to get a white marble? Well, that's just going to be the total number of white marbles over the total number of marbles in the bag, which is W over W plus B. So that's the probability of success. The probability of getting a 1 is equal to that. And basically, they're all exactly identically distributed. They are not independent. If this is 1, it's going to affect the probability that this is 1 as well. But clearly, because if you've got a 1 here, then there's fewer white marbles left in the bag for when you pick the second marble. They're not independent, but they are identically distributed, so their variances are all the same. Similarly, the covariances, there's a huge amount of symmetry there. Basically, the covariance of x1 and x2 is going to be exactly the same as the covariance of x3, x4, or x1, x5. Basically, it does not matter which you choose either, because they are just identically distributed random variables, and their relations to one another are completely identical. So in fact, all we need to do is work out one variance and one covariance, and then we've done this problem. So firstly, let's work out the variance of a Bernoulli random variable distributed with probability W plus B. So let's do that first. Okay, so the way we would work variance out is if we want to work out the variance of, let's say, to make it concrete, we'll say let's work out the variance of x1. This is going to be equal to the expected value of x1 squared minus the expected value of x1 times the expected value of x1. Right, so there's two ways you can view this. You can either view it as just the lotus problem, or you can view it as we create another random variable, which is going to be x1 squared. So basically I square this random variable, and when I do that, I get, again, two numbers. I get 0 and 1. So when I square 0, I get 0. When I square 1, I get 1. And again, what's the probability that you're 0? Well, that's exactly the same as the probability you're 0 here. And what's the probability you're 1? Well, that's exactly the same as the probability you're back here. So W over W plus B. So basically, the probability distribution of x1 squared, so x1 squared is still Bernoulli distributed with exactly the same probability, because the probability of getting a 1 is still W over W plus B, basically. It inherits the exact same probability as the original random variable. So if we take the expected value of x1 squared, that just means sum over every possible value that x1 can take on, x1 squared can take on. Well, that's summing over every possible value between 0 and 1. So I'll just put over x, where x can vary between 0 and 1. Of that value of x times the probability that, let's say, x1 squared is equal to that little value x. So if we perform this sum, we get firstly 0 times the probability that x1 squared is equal to 0 plus 1 times the probability that x1 squared is equal to 1. So I'm just computing this sum, basically. I'm saying x can vary over two values, 0 and 1, in this probability space, and the probability that it's equal to 0 is given by this, and that's not that we're going to actually need it, but that's going to be B over W plus B, because that's 1 minus whatever this probability is, and the probability that x1 is equal to 1 is going to be W over W plus B. Okay, so we get that this is just going to be equal to W over W plus B. So there's the expected value of x1 squared. Now let's calculate the expected value of x1. Well, it's exactly the same computation, because x1 squared is distributed identically to x1 itself. So if we want to calculate the expected value of x1, it's going to be exactly the same as this. But if we just say y, it's going to be the sum over all possible values that x1 can take on, which is again equal to 0 and 1, times the probability that x1 is equal to that value. So again, it becomes the exact same sum, 0 times the probability that x1 is equal to 0, plus 1 times the probability that x1 is equal to 1. Okay? And basically the probability that x1 is equal to 1 is again w over w plus b, and therefore we get that this expected value is equal to w over w plus b. So, if we work out what the variance is of this random variable, so if we want to work out what the variance of x1 is, we stick this into the formula, and we get the expected value of x1 squared is just equal to w over w plus b, and then we get minus the expected value of x1 all squared, which is w over w plus b squared. So if we pull that out, we get w over w plus let's pull out w over w plus b, and we get 1 minus w over w plus b, i.e. the probability of getting a 0, which i.e. what we might call q, which is equal to w over w plus b times, so I'm just going to leave it like that, times b over w plus b, so just working out what this subtraction is here. Okay, so that tells us what the variance of a random variable x1 is, and basically it's identical for any of them. So this is the same, the variance is exactly the same for any of those little subscripted random variables xi, basically. Okay, so we've done that. Now what we need to do is work out the covariance of two of these random variables. So we want to work out the covariance of xi with xj, but again, to make it concrete, we'll just say, let's work out the covariance of x1 with x2. Well, by definition, this is the expected value of x1 times x2 minus the expected value of x1 times the expected value of x2. Okay, so this is the bit that looks scary. This is the bit that looks as though it's actually going to take some work to figure out what that is. Well, if we, again, if we go back to our probability space up here, where we have these two random variables, x1 and x2, what we can do is we can construct a new random variable, which is from x1 and x2, we can construct the random variable which is x1 times x2, so we can construct that. And there are two possibilities, because x1 and x2 can both take on numbers between, sorry, this looks a bit of a mess. X1 and x2 can both take on numbers between 0 and 1. Therefore, if we multiply them together, if you multiply 0 with 0, you'll get 0. If you multiply 0 with 1, you'll get 0. If you multiply 1 with 0, you'll get 0. And if you multiply 1 by 1, you'll get 1. So you've got two possibilities, which are 0 and 1. So again, x1, x2 is going to be Bernoulli distributed. So x1, x2 is going to be Bernoulli distributed, i.e. it's going to ascribe to every single outcome a 0 or a 1. So to outcomes which were ascribed a 0 by x1 and a 0 by x2, it will ascribe a 0. To outcomes that were ascribed a 1 by x1 and then a 0 by x2, it will ascribe a 0. To outcomes which were ascribed a 0 by x1 but a 1 by x2, it will ascribe a 0. And only to outcomes that were ascribed both a 1 by x1 and by x2 will it ascribe a 1, basically. So it's going to basically ascribe a 1 to outcomes which had a white marble in position 1 and in position 2. So, if we want to find out what the probability of getting a 1 is, it's the probability of having a white marble in both positions. So, basically, it's the probability of, if you have a bag of marbles here, so let's have our bag of marbles. Firstly, you pick a marble out, and you get a white marble, and then you pick another marble out and you get a white marble. It's the probability of that happening. So, what is that? Well, it's we need to work out all possible outcomes that could happen. So if we make a probability space of what could happen, you're picking two marbles out of here, and imagine all the marbles are labelled again. So you've got 1, 2, all the way through to W here, and you go on to the black marbles where you've got W plus 1 through to W plus B here. So you've got all these marbles here, and you are picking a marble out. What are all the outcomes you could get? Well, in the first possible place, you could get W plus B total marbles, and in the second place, you could get W plus B minus 1 marbles. Now, that's the total number of possible outcomes here. Of course, that will take account of their order. So, in that case, marble 1 and then marble 2 will be counted as separately from marble 2 and then marble 1. That doesn't matter for us at the moment. We will because we'll just count order in both cases, basically. So now what we want to look at is what is the subset of this probability space which satisfies our condition that you get 2 white marbles. Well, that means that in the first position you could have got W possible white marbles, and in the second position you could have got W minus 1 white marbles. And that's why I'm saying it doesn't matter if we faff or not about whether order matters. Because in this calculation, again, order matters, but if order matters in both of them, it'll cancel out. If you're fussed about ordering matter, just divide by 2 to take away the fact that order matters, and divide by 2 here. But now, if we calculate the probability that you get a white marble, it's just the total number of possible outcomes in which you get a white marble, divided by the total number of possible outcomes of the whole experiment, which is this. And now the division by 2 basically just cancels out, and you get W times W minus 1 over W plus B times W plus B minus 1. Okay, and we'll cut this video short and continue in the next video.